I will be talking about rust in the skies over Antarctica. And before I do that, just a real quick introduction about myself. So I'm actually in astroparticle physics, a physicist. I'm working in the field since over 10 years, and basically since day one when I started with my master thesis, I'm doing coding on a daily basis. And during my time in the field, I've been in many places, and I worked on different projects, and I wrote a lot of different code. So starting with some personal analysis code, which I've written in Python. Then I got deeper involved into the project, switched to C++, and I've written code for like a lot of mass production, and so simulation and data processing, but also for little projects like little gizmos you have in the lab so that they can talk to each other when you have to do some local measurements in the lab, and also wrap that all up and write web applications for the lab so that people can easily use all the different instruments. So I had quite a journey, and recently, basically more precisely last year, I got into Rust, and at the same time I was tasked with a really critical part of the project I'm working on, which I'm gonna tell you here in this talk. And the nice thing was, so I got really excited when I was trying out Rust for myself, but at the same time I figured this is exactly solving the problem I have to solve for my project. And before I tell you about the project, I have to start at the beginning. So we're not exactly going back to the Big Bang here, but we're looking at the universe. So I told you I'm an astroparticle physics, a physicist, and what I'm actually studying, what my main task is, so we're looking into dark matter. So we're pretty good in our understanding of the universe. So actually, we have very precise theories how everything works. However, if you look closely at the theories, actually turns out we don't understand so much. So what happens is we're pretty good in weighing stuff. So we can determine basically all the energy density, like the mass of the universe. But then if we look closely and we look what is the things we actually see in the universe, like individual stars and galaxies, then we actually figured that doesn't add up to the mass we're actually measuring. And we can do this on a lot of different range scales in the universe. And I have two examples here for you, so I will walk you through it. So in the bottom left, this is actually a very famous picture. And in this picture, what you see, there's two galaxy clusters, and they're actually traversing each other. So they're kind of colliding. And it happens that in these galaxy clusters, actually, the most luminous matter, the matter we can see with telescopes, or in this case, it's actually X-rays we observe, comes from gas. And when these two clusters collide with each other, then this gas heats up and emits X-rays, and this is the pinkish color in this picture. So what this shows you is that, I'm sorry. Okay, sorry for that. I won't do that again. So what that shows you is the most mass we see is actually centered around this pink dot. But we can also apply a different technique to detect mass, which is gravitational lensing. And this, if we apply this technique, I don't want to go too much into the details, but we see that there are actually two centers of mass, which are indicated by the blue shaded areas. So what this means for us is that actually the stuff we see, and actually the stuff where it's like the most mass, they don't line up. So actually what happened is like there's something in these galaxy clusters which when they traversed, it actually didn't interact at all, we didn't see anything, but it seems to be there. And another very famous example is the rotational curve of stars and galaxies. So this is in the right. So you have two stars, so one is very close to the center of the galaxy, one is further out, and if you imagine the galaxy as like the swirl of stars, then what you actually would expect that the stars which are further out, that they rotate much more slowly around the center of the galaxy. Like if you imagine our solar system, also the outer planets, they rotate much more slowly around the center, but it's also not what we observe. And in conclusion, we think the galaxy must have something in there which is like heavy, but we cannot see it. So, and now the thing is, I told you like I'm in this field and we want to detect it, and how can you detect something you cannot see? Well, the thing is, we have no clue, but it doesn't stop people from coming up with theories. So, and kind of the hope is, or the idea is, that eventually these dark matter particles, let's say it's a particle, it will interact with each other, something will happen, we don't know what, but in the end, it will end up producing something we can actually detect. And in this example here, it might be all kinds of particles, and where do these particles then will be happening? So I showed you like this is something from outer space, so actually there will be a flux of these particles somewhere in space. And what happens to us on Earth is actually that we get bombarded every second by a lot of these particles. So these are all kinds of particles, elementary particles, electrons, hydrogen, nuclei, and so on and so on. And now the difficult task is we have to figure out which of these particles come from our dark matter interaction. And here, so with the experiment I'm actually telling you about now, so we exploit a trick. So some of these theories which say that this dark matter particle will decay to particles we actually then can observe, they predict that it will produce matter and antimatter pairs. And antimatter is the same as matter, it's just oppositely charged. But the thing is, what is important here, is very rare. So if we see some antimatter among all these particles which coming from us from outer space, then we might have found a hint that this dark matter exists. And so how we would identify such particles? Well, there are a lot of experiments. The one I'm working on is called GAPS. So GAPS stands for General Antiparticle Spectrometer. It's a particle detector. It's pretty big for what it is. And it's going to be hooked up to a balloon. And I tell you about that in a second. First, I want to tell you how you actually measure such particles. So there are two properties which are very important so that we can figure out what type of particle we're actually measuring. And these are the velocity of the particle and the energy. And so for these two properties, our detector has two components. The one which measures the energy is called the tracker, so we don't talk about this here. What I want to talk to you about is the TOF system. TOF stands for time of flight. So what you do is you have two planes of detectors, and actually when your particle is traversing, then you measure a timestamp when it traversed the upper plane, and you measure another timestamp when it traversed the lower plane, and you know in which distance you installed your planes, and then actually you can calculate the particle velocity. And how you do that is, so in particle physics, we like to use something which is called a plastic scintillator. So it's actually just transparent plastic, and what happens when a charged particle traverses this plastic scintillator, it scintillates. So it produces a little bit of light, and this light you can detect. So there's a picture in the bottom of one of these scintillators. You can't actually see it because you have to wrap it very well in this dark plastic to shadow it from the ambient light. So, and in the bottom there's a picture of the actual experiment. So this is the thing we're going to hook up to the balloon. So you see what you see in the top is like one of these planes for this time of flight system I was just telling you. And it's like, it would fit in this room, but for a balloon, it's rather big. So then the title of my talk is Rust in the Skies over Antarctica. So now I hope I have gotten you excited about what we want to measure and why we want to measure it. And so now is where do we want to measure it? And the thing is, these particles, I was telling you, they're coming from outer space. So you have to go either to space or at least high up in the atmosphere. And Antarctica is a really good place for that. First, a very basic thing, logistics is really good in Antarctica. It's easy to get science experiments shipped there, relatively easy, or more easy than you would imagine, because what you see here, the aerial view is a view of McMurdo Station. It's a large, not a settlement, but a large science station which is staffed full year. And they have a population of about 1,000, so there are a lot of people who can help you launching your balloon. And so this is one reason, so it's actually doable for us. And the other two things are, so first, if you have a balloon, you want to have stable weather conditions. So you want to have your balloon going for a long time, we hope for 30 days. And that means it needs like a stable atmospheric conditions. And it turns out that around the South Pole, there's a jet stream. And so we hope we can catch this jet stream. It's in about 37 kilometers height. And then if we catch it, is hopefully stable for around 30 days. And then there's another very important property for us, which you have at the poles. So if you look at Earth's magnetic field, then so around the equator, so the Earth magnetic field is parallel to Earth's surface. So what you see here in this plot is the strength of the magnetic field parallel to the surface. And if you go to the poles, then actually it curves, it bends, it gets inside the magnetic poles. And that's where like actually particles will not get deflected by this field anymore too much. And so they can reach these layers in the atmosphere we can send our balloon to. And that is actually the same effect why you see the northern lights. So if you have a balloon, there's some specific challenges, and now we come more to the software part of the talk. So actually on a balloon, you're limited with everything. So first you're limited with your weight, so it can't be too heavy, otherwise it won't lift off. So we're already rather heavy, so we're around 3.7 metric tons. But there's also other things which are limited. For example, your bandwidth, so you don't have an infinite good connection to your balloon, so you have to be very careful what data you want to send down. And also there's another thing which is really limited, which is power. So the balloon has a solar array, and it just can generate a certain amount of power, and this cannot be exceeded. And then if you think now you have to write a code for this balloon, and you look at programming languages, so the thing is, because you're so limited, you still have a lot of science to do on the balloon. So you have to still crunch a lot of numbers and do a lot of tasks. And you can express the ability you're able to do also in terms of the amount of energy you consume. And so I got this picture from a publication, and what these folks were doing, it's really a great publication. I can also put that in the Discord if you're interested. So these folks were studying, so they were benchmarking different programming languages. So on the x-axis, there's just the name of the programming language. On the y-axis, there's how much power it consumed for a very specific task. And they did a lot of benchmarking, and in this case, it's walking through a binary tree. And so you see that actually like our beloved Rust is doing really well. So this is really great. So just if we had chosen Go for our project, where we could have gone only 6 times less stuff done on the balloon. So this, in this way, is already a consideration you have to make if you write code for such a project. Now, finally, I'm really happy that I have a penguin on my slide, which was promised. So for this balloon, we had to construct a lot of electronics. Everything is custom-made. I don't want to go too much into detail. So this was developed at UCLA, and they did a really good job. I just want to highlight 2 electronics boards. So it's the upper 2, the red one, and the one in the middle. And so the red one is part of the trigger system. So I have to mention the trigger system a few times, because the trigger system, what it does, so you have all these scintillator pedals. So actually we have 160 of them, so it's quite a lot. They're arranged in these planes. And what your trigger system is doing is telling you which of these pedals actually have seen something interesting. So where did the particles traverse through? However, this trigger system, that has to be really fast, so that it's all done on a level which is firmware based. So with our software, we don't have any access, we just get some bit mass from it. And where now the software I want to talk comes into place for this readout board part, so the middle one. So this is actually the part which does digitization of the signal. So there's a digitization chip on there, but there's also a 30-bit ARM chip. And actually it's done in a very clever way. So the result of the digitization will be laid out in the memory the operating system can access. And then actually with our Rust code, we can directly access our digitized data in this board and then start processing. And this runs Linux, so there comes the Penguin. So there are other components. So actually, these readout boards we have a lot because they connect directly to these pedals, the scintillator pedals. But then all the data from the readout board gets further processed in a central instance, and that is an embedded system that is so some off-the-shelf component we just bought. And this talks to all the readout boards over the network, so also this requires a lot of coding. And then we have another component. I already mentioned this red board, which was part of the trigger system. This is also controlled by a master instance. So this is also some custom electronics which was made at UCLA. And all of these components can talk over the Ethernet with each other. So just to sum all this electronics up, so this is a view of like the data flow. So these are your individual components. So you have these individual scintillator paddles, which basically produce an analog signal. Then they're connected to the trigger system, and they're also connected to a readout board. And in the end, everything gets gathered by the central CPU, that's the central embedded system, and it gets passed on the chain, and it gets the other consumers on the balloon, and finally, so it also gets stored, and finally it gets sent to the ground. So now I was actually talking a lot about signals and analog signals and digitization. So here's what our signals actually look like. So I told you about these scintillator paddles, and I told you that there's light emitted in these paddles. And so now the question is how you detect this light. So actually what you do is you have very sensitive kind of photodiodes, and you put them on each end of the paddle. And these photodiodes, so they are semiconductors. So what happens if you shine light on them? There will be a current in this. So if you apply voltage, there will be a current, and then you actually can measure voltage drop. And this voltage drop is our signal. And in a digitized form, you can see this in this graph on the bottom. So in the x-axis, you have nanoseconds. So it's actually quite a very fast signal. And on the y-axis, you have millivolts. And this is the signal we get on our readout boards, and then now we have to process it in the first stage. And actually, there already comes the first problem, because the signal is rather big for us, because you have 1,024 values on the x-axis, and each of these values has 14-bit. So it's a pretty good digitizer, but it means we have a lot of data, because you have to imagine we have 160 paddles, each read out on both sides. And that can be, for our limited balloon, can be quite a lot. And that is actually where the project I'm talking about, where it started. So I was assessing the software which was developed for the balloon. And then it turned out that in a way, because this trigger system and the readout system were not inherently connected, so it turns out we're just trying to read out everything. And then you quickly run into a problem, because I told you it's a lot of data, and I told you also we're limited. So our network switch is only 1 gigabit per second. And so this limits the rate we can detect particles with, where you have to read out everything to about 170 hertz. And that was not fulfilling our science requirement. So the science requirement is something more like 500 hertz. And another thing is, with this 170 hertz, also it's already super saturated, right? You do not want to use like all your headroom. And so this was a big problem. And then so it was assessed. And so there are two ways you can tackle this problem. One means actually you use this trigger system and only get data from these paddles which have actually seen something, or where the trigger claims they have seen something. And the other way is you take your signal and you compress it somehow. So you extract values which are interesting to you, or you cut it down somehow. However, there you have to be very careful, because there's a lot of information in this signal. And also for us, because we're looking for something new, like ultimately dark matter. So we don't know actually what we're going to see, how our actually signal of when the particles appear in the detector. We have to be very careful. We can probably learn a lot from the signal, so we don't want to cut down on that too much. So this kind of solution, so we have to work on filtering and in many ways, but this means we have to really run elaborate code which does all this on our TOF system. And besides this, the code has to perform other tasks. It has to do the data acquisition, so just in general, just also save the data, check integrity, maybe calculate a checksum, and then there's also a command interface, so people on ground want to send commands to the balloon, so this has to be processed, and also some other tasks you have to do with these detectors, like calibration and such. So there are many things the code has to be doing. And so I want to tell you now actually why Rust helped me to overcome all these issues and all these major problems. And for me, it's really great. Just by coincidence, at the same time I got introduced to the project a little bit earlier, I just played around with Rust and I really liked it. I thought like, oh, this would be great if I could do a real project with that. And then this landed on my desk. So this was really great. And there's one thing which actually really helped me out is that, so in academia and the working groups, they're usually pretty small. So the task, I'm telling you, like this compression of the data, this is mission critical. So if we don't achieve this, we don't have to fly. So this is absolutely crucial. Also the velocity measurement that this works, this is crucial for the mission. So I felt like, okay, I have this humongous task and now I need help, but at the beginning, there were nobody else, but actually Rust was really friendly and helped me with that. And so I have a list of things which really stood out to me. The first is multi-threading. So I told you we're limited. So this also means still today everything is multiple cores. Even on the readout board, we have 2 cores. We have to use all these cores concurrently. And Rust was really friendly. And actually, in this code, I'm still using the threads from the Rust book, from the example, and they're still performing very well. So this was great. Then another thing, which these are little things, but yes, that's a big deal. So I/O. So I told you we have all these different components which have to talk over the network with each other. This means we have to do serialize our data structures. We have to serialize them to bits and bytes. Unfortunately, I'm a little bit dyslexic with that, but also there, Rust was really friendly. So in the standard library, you have these beautiful methods to little endian bytes. It was very easy or comparatively easy to write parsers which actually would do the job. So you can immediately ask, why didn't we use a serialization library? The thing is, we decided really to go completely custom here to really squeeze out everything of the resources we have. Then another thing which is really important is error checking. So Rust's result is great. So it really fits our needs. So when you're on a balloon, so this balloon is basically operating autonomously. Since the network connection is so limited, there's decisions it has to make by itself. And result really helps for every step in the code. That's how we coded it. For every function call, you get a result, the code checks, okay, what do I do now? Okay, what happened? How do I mitigate this problem? And even if we don't know yet what to do, it at least will write a log entry. So when when working with the code and analyzing how it performs and what are the issues, we will know. And I don't have to say that, but also panics are not allowed on the balloon, and working with result that really helped to mitigate that. Then another thing are tests and benchmarks. So as I was starting this project by myself, there was not really anybody else who would like write tests for me, and I was kind of under time pressure a little bit to get stuff going. And their cargo is really friendly, and the environment it provides for you for tests just make it very easy. And this code is mission critical, so this means that I cannot make any mistake. And I don't have any, or at the beginning at least, I didn't have anybody looking over my shoulder, so I totally rely on tests. But we're supposed to fly next year, it cannot take a lot of time, so it was really appreciated that it was made so easy. Benchmarking is another thing. So I try to have the code first in a simple way so that I understand what I'm doing even after a few months. But since the resources are so limited, I do need to do some benchmarking and see if I can achieve the goals I was tasked with, and this was made very easy by Rust as well. This is basically the end of the technical part of the talk. So I want to tell you a little bit about my experience with Rust in the astroparticle physics community, or at least in the community of the experiment I'm working on. And so this was the first Rust project actually within this group. And so before that, or basically what is the situation at most working groups in astroparticle physics, at least from that what I've seen over the years I've worked with them, so most code is C++. And this is basically, I think it has two major reasons. One is that big libraries which many people rely on, which is this root and the Geant4 library. So root comes from CERN and provides a really good input-output interface. And actually CERN stores all its data in this format. And Geant4 is a library which is very popular for simulating particle interactions in matter. So they are written in C++. So most people want to interface with that. And the other issue is that working groups in academia are typically really small, and they're under a lot of pressure to publish, and so people simply usually do not have the time to spend time learning something new. There's some code somebody wrote a long time ago in C++ standard 98, and it still works, so you're pressured to kind of use that. And how was the situation for me then? So actually, as I told you, I just started out of curiosity with Rust, this project with Rust, and I quickly figured that it actually ticks all my boxes, and this might be the only way actually I can achieve this task. So people were actually really friendly when I told them. So I recently presented this at our collaboration meeting, and I only got positive reactions. So I was expecting maybe a little bit more backlash, or that somebody says like, oh, why don't you do it like we always did it? But that's not what happened. So I want to encourage you, if you have a new project and you want to use Rust, even if you're in an environment where it wasn't used before, maybe it's worth to take the leap. And a few things the community can still do for us. So I don't know, this is not, I'm not asking for this, it's just my personal opinion. So what Python did, they've provided a package which can read root files very easily without depending on all this root library. And I think that was kind of a breakthrough for Python in my field, or not the breakthrough for Python, but it certainly helped with the adoption. That you can easily read these root files. So this was very helpful. I really like Polars. They're certainly helping. So Polars is a Rust data frame library that's certainly helping. Yeah. With that, I come to my conclusion. And so this is my summary. I hope I got you a little bit excited about the GAPS experiment and the search for dark matter. And I hope I could convince you that Rust is a perfect fit for this task. And it's actually going to go up and fly and circle in Antarctica or in the skies, hopefully next year when our balloon launches. And yeah, with that, I want to thank you all, and thanks for tuning in to the stream. And yeah, thank you.